Okay. All right. So we're very pleased to have Daniil Rudenko from the University of Chicago, and he's going to tell us about polylogarithms, algebraic K-theory, and the Steinberg model.
Thank you very much for inviting me. It's a great honor to give a talk here. So the talk will be about polylogarithms and Goncharov program and some new conjectures and some new results about it, all related to Steinberg module. Actually, there are two works I'm going to talk about. So there is a joint project with Charlton and Daniil Radchenko, and there is a preprint which just appeared a few days ago on arXiv, and there is a work in progress with Ismael here and Alexander Kupers, which we will hope that will appear in a few months. So I want to start with discussing a little bit Goncharov conjectures relating multiple polylogarithms and algebraic K-theory. And these conjectures are not completely precise in some parts, so it's a little bit of a sketch. But I want to do it for motivation and then explain some more precise conjectures we have now about that. So let me start with a very brief description of what we might be interested in doing from K-theory perspective. So suppose F is a field, so arbitrary field, and then we can talk about algebraic K-theory of a field, and I will be interested at the rationalization. So algebraic K-theory tensor Q, and for algebraic K-theory, I think one can say that more is understood about torsion maybe than about rationalization. So that's interesting. And for small n, there is explicit description. So for n equal to 1, for n equal to 0, that's just q. I mean z tensor q. For n equal to 1, this can be identified with multiplicative group of a field. And for n equal to 2, there is a computation Yuto Matsumoto. So there is a completely explicit description. You need to take base square of abelianization of the field, a multiplicative group of a field, and then quotient by so-called Steinberg symbols. Everything tensor Q. And the goal is to get something as similar as possible, as explicit as possible for higher n as well. So let me say up front that completely satisfactory solution only exists for n equals 3, but I will mention results about n equals 5 as well. And there is a conjectural picture for all n and all fields. But this picture is maybe a little bit speculative, but I will try to explain that. So the idea is that there is expected to be a connection between algebraic K-theory and a special function called multiple polylogarithm. So let me define what that is. So multiple polylogarithm is a following function. So we have a collection of variables which are complex numbers of that absolute value less than 1. And a collection of maybe k, and a collection of integers. So and 1 and k are just positive integers. And then one can look at the following power series. So it's a sum. It's a power series where you just take monomials in variables z1 up to zk divided by powers to a degree which is equal to these numbers, and you sum up over a cone an infinite simplex which looks like an autoscheme. So that is a multiple polylogarithm. And the simplest example, so there are two parameters here. So one is called weight. This is n, which is a sum of this indices. This is weight, and this is related to motivic weight, and it's kind of more clear why it's important. But also there is another parameter which is called depth, which is a number of arguments. And these functions have a property that when you when you look at functions at lower depths, they can be obtained by degenerating functions at higher depths. So you could think of it as kind of a more and more specialized function of less and less number of variables. Of particular interest is classical polylogarithm function, which is Z. So these functions are interesting in various regard. And so one thing which will be important for the next several minutes is that they satisfy lots of functional equations. So one should be a little bit careful because this is a multi-valued function. It has monodromy, and monodromy is pretty complicated. So for simplicity, I will assume that I'm working modulo products. So there is a technical way to say it. You need to discuss the associated framed variations of mixed Hodge structures. But I will ignore that. I would just think that kind of products of similar functions of lower weight goes to 0. And in particular, the monodromy of such function is of type 2 pi I times similar polylogarithms of lower weight. So I ignore that as well. So after I do that, I can start talking about equations and just a few examples on the left board. So this is the most famous 5-term relation for dilogarithm. So the terms here, equation by equations, I mean you take polylogarithms and you sum them in certain algebraic, their argument should be some algebraic functions of a bunch of variables. So this is a 5-term relation where these 5 points are actually cross ratios of certain 5 points on P1, found by Abel and has very interesting theory, history. And then equation on top is this 22-term equation for trilogarithm found by Goncharov. And that is the one which, I mean, I will try today to explain a little bit of where it comes from, sort of conceptually. And also have one more equation which I will discuss later, so let me not come to it. But it's just like an idea of what kind of equations you might have. So now the idea is that there should be a way to, if you understand well equations for multiple polylogarithms, to write down an explicit complex whose homology will compute algebraic K-theory of a field. So this is what Goncharov conjectures predict. And let me try to state, I mean, just one version of this picture. So Goncharov conjectural, let me say conjectural picture because there really no precise conjecture, because at some moment I will say something like all equations, or which is not clear what it is. But anyway, so this picture is actually based on lots of previous work. So there is a very important work of Don Zagier about the relation between special values of zeta functions of number fields and classical polylogarithm. Then there is this work of Bellinson and Bellin, which reinterpreted it from the motivic perspective. And then most of this work was kind of with a view of the case when F is a number field. And then kind of Goncharov made a bunch of conjectures which basically don't assume F is a number field for arbitrary field. And I will explain basically that shape. So the conjectures are basically, the picture is as follows. So for a field F, there should exist a graded Lico algebra over Q. So this is, let me call it L of F. So this should be the Lico algebra, the fundamental Lico algebra of the category of mixed state motives over the field F. But not to get into that, I will kind of stay within this polylogarithmic kind of realm. Maybe I will later mention why. So there should exist a graded Lico algebra L of F with the following properties. So firstly, for every collection of points, maybe x1, x3 in the field, and every collection of integers, you should have an element in this liquid algebra, which is, I mean, notationally looking like multiple polynomials. So I will put the word M here for motivic, meaning sort of corresponding element of this liquid algebra. And it should even with M. And moreover, so you should have that, and this L is expected to be spanned by these elements. These elements span L as a Q vector space. So you have kind of a collection of elements which are generators of L, and then the relations between these elements should be some or maybe all or kind of universal equations satisfied by polylogarithms. So these elements satisfy polylogarithmic equations. This is where it's not particularly clear. What I mean, there are various ways to make it completely precise, and I mean they're all not that interesting because I think the actual hope of Goncharov was that you can actually write down a very explicit equations, very simple equations, one in each weight maybe of the type like this 5-term relation and this 22-term relation, and that would be enough. But let me not precisely say that. So this element should satisfy some universal equations. And then so the third condition.
This type of equation is evaluating at some rational function.
Yes. Equations of the type that you have sum of multiple polylogarithms of certain rational arguments. Maybe I will allow like roots or something like that. So
you have roots.
Yes, I would. I mean, I think this can be rationalized. Actually, you can just take squares. But let me not. So I will later make a way more precise conjecture where this issue will not be present. But so the third condition is that actually I said it's a liquid algebra, so there should be a formula for co-bracket. So co-bracket of this multiple polylogarism element. So there is a predicted formula for it. So I'm not able to write it because it's actually combinatorially a little bit involved, especially for general multiple polylogarism, but I will write it for classical polylogarism. So for classical polylogarithms, the expected co-bracket is given by the formula that it's for n equal to 2, that's logarithm x, which logarithm 1 minus x. And for higher n, it should be minus 1 of x, which logarithm x. For n greater equals n 3. I change the sign. And there is an explicit combinatorial description of the co-bracket, which you expect in general, which is motivated by the fact that multiple polylogarism is a period of a certain mixed structure, and you can analyze it, and that is the origin of this co-bracket kind of computation. And finally, of course, the connection with algebraic K-theory should be as follows. So that's kind of maybe the main conjecture is that if you take cohomology of this liquid algebra, just with rational coefficients, and by that I mean cohomology of the cobar complex, and then you take kind of weight n part. So this algebra is graded, so you can look at weight n part. So this is expected to be isomorphic to graded piece of algebraic K-theory of the field, and the weights are weight n. So you should have 2n minus I nth piece of gamma filtration rational. So explicitly, that would mean that if you know L is presented to you by generators and relations, you can expect that you have a very explicit description of algebraic K-theory, in particular, the part for I equal 1, which is the only one present for a number field, would be given by kernel of a map from L to something, and elements in this kernel can be explicitly constructed, and one can compute with it, so it's very explicit kind of object. So if one has something like that, that would be very good. So maybe there is maybe let me add one more kind of conjectural piece. So for n equal 2, so for n equal 1, for what happens for small n. So for n equal 1, you expect that L1 is just f star tensor Q, and this is just predicted by this computation, because in this case, this Kobar complex has length 1. So just get that. So for n equal 2, you expect that this is, so this should have generators given by polylogarithms of weight 2. And theoretically, there are two of them, Li1, 1 and Li2, but there is a formula relating them. So everything can be expressed through Li2 through dilogarithm. And so this L2 is supposed to be a Q vector space on elements of the field, which I denoted kind of dilogarithm of X, subject to this 5-term relation. So that is sort of suggests that actually every functional equation for dilogarithm should be a consequence of this one, which is true for equations with rational arguments by a theorem of Suslin and not known otherwise. And finally, for weight 3, you also expect that actually it's so you can similarly express every polylogarithm through trilogarithm, and you expect that the only relevant equation is a 22-term relation which I wrote on the. So classically, these two groups are denoted by B2 and B3 and are sometimes referred to as block groups or pre-block groups, two conventions. So these are the conjectures, and so the main problem which we had in this area for a long time was that it's actually very hard to guess what are the correct equations for higher weight polylogarithm, and also that any motivation behind these conjectures and relation with algebraic K-theory goes through the theory of motives and through connection between algebraic K-theory and motives. And the only known result, which is kind of definite in this direction, is actually a theorem of Suslin. Maybe let me also say that. So there is a theorem of Suslin, which theorem due to Suslin, which shows that actually this holds for L2. So if you take L2 and look at the map to H2 of L1, so maybe let me say more explicitly, you take B2 of F and take a map to H2 of F star, which is exactly the co-bracket, and so that this complex is exactly the weight 2 complex as predicted here. So if you take this this map, then it's easy to see that the co-kernel of this map is mu of K-theory. But also there is a kernel, and the theorem of Suslin shows that it's actually K3 indecomposable of a field. And here I assume that everything is tensor Q. So integrally it's not correct, but rationally it's correct. So this K3 indecomposable is exactly the same. Tensor Q is the same as the graded piece which I wrote there. So for weight 2, this conjecture kind of is a theorem essentially. But already for weight 3, you can absolutely write down similar complex as predicted by Goncharov. And in his work from early 90s on the special value of zeta function, Zaghi conjecture for special value of zeta function in weight 3, he analyzes cohomology of this complex. He compares this with K-theory. One can construct certain maps from K-theory to cohomology of this complex, but whether they are isomorphisms is not known, especially here. So, but you kind of expected that this is what appears. So that was a little introduction in this picture which exists from early 90s. And now I want to, if there are any questions about that.
So what is NZ related to motif, but it's using the Dharma analysis?
I mean, I think that literally, if you want to get this function as a period, you can look at the Raman materialization, you can look at comparison metrics, and you will see that as one of the coefficients. Yes.
So I'm just to get the, so B3 is connected to K5.
So you expect that to be a graded piece of K5, and you expect the third graded piece of pressure.
All right.
And here K4 and here K3, but always third graded piece. Okay, so now let me completely switch gears and let me just say briefly define for you Steinberg module. So that's unlike all that, it's a completely explicit and elementary object. So so a Steinberg module is the following very, very classical object. So Steinberg module.
Maybe you said this, but if you have an element in this kernel of B3 to dot, can you construct an element in this graded piece of K theory?
If you assume motivic formalism, then yes. Because
what are you assuming when you say
so
that?
if you know that the category of mixed state motives exists for a field F,
I see.
for instance, for number field,
Okay.
then you can use all these results to construct it. On the other hand, map from K theory here, which constructed by Goncharov, is kind of much more elementary. It sort of goes through some group homology techniques essentially. So my goal would be sort of to okay, let me just let me not say what is my goal. Let me do it. So a Steinberg module. So this is completely elementary notion. So I take a vector space V, is a vector space of dimension n over a field. And then I can define the Tits building of V. So this is a simplicial complex. So this is a simplicial complex where P simplices are partial flags of P plus 1 of length P plus 1, and I mean of proper non-zero subspaces. Of proper non-zero subspaces. So your points are actually proper non-zero subspaces, edges are pairs of embedded proper non-zero subspaces, and so on. So then the Steinberg module of V, which I will also maybe sometimes denote Steinberg n of F. So if your field is your vector space is F power n, so this is the top homology of the space. So Tits building is known to be homotopy equivalent to bouquet of spheres. That's a theorem of Tits and Solomon. And so you can look at the top homology. Let me give a more elementary way to think about this object because it's completely elementary. So firstly, maybe an example is if you take n equal to 3, then your Tits building is actually incidence graph of P2, meaning points and lines are vertices and edges point lying on the line. So it's a graph, and this Steinberg module will be in cycles in this graph. And how to construct an element in the Steinberg module? So if you have any collection of vectors v1, vn inside your vector space, then there is a special element called an apartment, which is denoted like this. So who is that? I mean, explicitly, you basically take. So let me do an example maybe. So you take for instance, in P2 to a triangle, you can associate a certain linear combination of flags, where you take a flag containing a vertex and an edge of this triangle, and you sum up over all such flags with signs. So you will literally get a cycle inside the. You will get a cycle in the shape of 6-gon inside your incidence graph. And in general here, so you can take sort of sum of -1 power sigma over all permutations, and then you do flag where you have v of sigma of 1 contained inside v of sigma of 1, v of sigma of 2, and so on. So in this way, every simplex determines for you an apartment and an element in Steinberg, and they satisfy a bunch of relations, which are all quite easy to define. So there is a relation that this v1, vn, if you take v1, v2, vn, and if you rescale any vector by lambda, that doesn't change. So actually it only knows the projective geometry picture, which is kind of evident from the definition, which never uses, which only uses kind of chains of subspaces. And also you can of course relabel the vectors and you acquire sign. And finally, there is last relation, which is that if you take one more vectors and determine a simplex, and forget one of those, with the signs you get 0, which means that if you take, let's say, triangle subdivided, the triangle is the sum of its pieces. So I would think about it as kind of a Caesar congruence in a vector space without a group. So that's my picture of Steinberg model. So very elementary. And one more technical observation is that Steinberg module has a structure of an algebra of some sort. So there is a way to externally kind of multiply elements of Steinberg module. So if you take Steinberg module of a vector space V1 and Steinberg module of a vector space V2, there is a product map to Steinberg module of vector space V1 plus V2. So it's just concatenation of apartments, and you can just it's kind of, it looks like a join of simplices geometrically, but sorry, no, it's not even a join. It's just literally concatenation. You have a bunch of vectors in one space and another. You embed both, and you can take all of them at once. So so now I need a definition which is completely elementary, but can seem a little bit not particularly well motivated. So I mean, you have this property as this map on Steinberg. So you can, of course, just take a tensor square of Steinberg module, which, I mean, so it will be important in the talk. So tensor square of Steinberg module, of course, it's just a tensor square of Steinberg module, but a geometric picture to have in mind is kind of pair of simplices in projective space. That may be helpful without any restriction on general position, just arbitrary pair of simplices defines an element there. And then, of course, if you have this product, you can also, I mean, it also would exist for tensor squares because you can just diagonally multiply elements in each Steinberg. So this is also kind of an algebra in this exterior kind of sense.
So it's associative in the numbers. It's associative.
It is associative, and it's even greater commutative.
Ah.
Yes. So now definition, which is completely, still completely innocent. So Steinberg L of V is by definition the following object. I take the Steinberg square, so I take the pairs of simplices, and I kill all elements which come from this product construction. So I take the sum over all decompositions of V into sum of two spaces, which are both required to be non-zero. And then I take the Steinberg tensor of V1 and V2, and I can multiply them to get an element in Steinberg of V, and I take the co-kernel. So the way to think about it is you are now taking all pairs of simplices up to the Caesar congruence relation, but you put some of them equal to 0, those which come from decomposition of your space and kind of from similar pictures in lower dimension and kind of product. So to be honest, you can completely ignore till the end of the talk. You can think that this is just Steinberg tensor Steinberg. For intuition, you will not lose much. It's extremely close to Steinberg tensor Steinberg. So now let me formulate the main conjecture. So maybe we do it here. So the main conjecture, which is first might look a little bit strange. So conjecture, and that is with First and Sierra and me. So the conjecture is that this Lico algebra of mixed state motifs, or this Lico algebra of multiple polylogarithms, this Lico algebra I discussed before is literally the first homology of GLN as a group with coefficients of F, with coefficients on this in the Steinberg module L of F. So that is the main conjecture. So
this comes with the construction of the polylogarithm element.
Right. So I will say in a second what about this conjecture I can explain or prove, or because so at first nothing is clear here. So firstly it's so it's an elementary object. This is a elementary defined module which is related to Steinberg module. This is a GLN group. This is first homology is a group homology. So it's a It's a completely elementary object. But what is not obvious about it is it's not obvious it's a liquid algebra. The co-bracket there is not evident. It's not obvious that it's a question of how to construct elements there, and of course that they're connected in any way with polylogarithms or equations is not obvious. So in a sense, a priori it comes extremely unmotivated.
I have a little trouble with your notation. So what is the exponent at ST?
So here is L, which just symbolizes, that's for liquid algebra, it's a bad notation. That's that object.
Yes, but then what is the exponent then?
So here,
Yes.
so this is Steinberg squared, just tensor squared. Yes, just Steinberg squared. So in a sense, you can think this is very close to first homology of GLN with coefficients and Steinberg tensor Steinberg, but slightly modified Steinberg tensor Steinberg. That's the conjecture. And it's not a priori. There is no single reason for that. Maybe let me make a quick comment. So there were conjectural elementary descriptions of this liquid algebra, and for instance, there was one by Beilinson, Goncharov, Shachtman, and Radchenko in terms of pairs of simplices. So there is a multi-polylogarithm and pair of algebra where generators are pairs of simplices, because to a pair of simplices you can associate a mixed state motive in a natural way, and so there is kind of a version of this story there, which was there from 90s. So the difference between this construction and that is that, so here you allow arbitrary degenerate pair of simplices, whereas there it's very important they're non-degenerate, they're in general position. But the price is that if you take H0 here, it will be trivial. I will talk about this result in a minute, but here you take H1 for some reason. So that's somehow strange construction. So, but maybe let me mention briefly what we can prove about it. So this is in a work which is not yet fully written. We hope maybe in a month or two. So what one can do, so firstly one can construct, so there exists a co-bracket on this direct sum of H1 GLN Steinberg and L. So there exists a canonical co-bracket there. This we can discuss. So this is a liquid algebra, indeed. So then the second property is that there exists a family of elements there which looks looking like very much like multiple polylogarithms. So there exists a family of elements there, and firstly, one can show that you can describe all equations between them explicitly, and these equations hold for polylogarithms. So there exists a realization of this in the corresponding liquid algebra of mixed Hodge structures, for instance, or motives, if you assume that they exist for F. And moreover, the co-bracket on these elements coincides with the one coming from the theory of mixed Hodge structures and predicted by Goncharov. So we can compute this abstractly defined co-bracket, and it is given by a correct combinatorial formula. But maybe most kind of nice thing is that actually one can show that for n equal 2, this H1 of GL2 Steinberg 2L is actually the B2 of F block group, which is actually not a hard computation. It's pretty elementary, but much more interestingly, if you take weight 3, then actually you can prove that it's exactly what Goncharov predicted. So it's exactly the B3 group. In particular, you can see how the 22-term equation appears from basically topology, from very group homology arguments. You don't need to assume anything. You don't need to do anything with it. So these are kind of some results which I hope will be available soon. But today, in the rest of the talk, I want to explain how to construct a map from this H1 to polylogarithms for a field being Q. So for a field being Q, so F equal Q is, for some reason which I don't understand conceptually at all, is a very, very special situation where we have a lot of extra nice intuition. And basically, though the proofs here exist for arbitrary field, the constructions are absolutely unmotivated, to me at least. And for a field equal Q, one can kind of understand everything in a nice way. And that also kind of is interesting for separate reasons. So I will switch to F equal Q.
Can you tell us a little how you discovered this conjecture?
Right. So the story was that we were working with my other collaborators, Steven and Daniil Radchenko, on the field equal Q case, not of this conjecture, but just in general, kind of on the Steinberg module for Q. I will explain in a second why. And as one of the results, which was a consequence of our results, we proved that H0 of GLM Q Steinberg and LQ is equal to 0 for n greater or equals than 2. I mean, we didn't state it in these terms, but that came out of the work. And then at some moment, I met in a conference Alexander Kupers. He explained to me that this result actually appeared a few years ago in the paper of Kupers, Galatius, and Randall Williams, motivated by work on Rogness conjecture. And then we started to kind of compare the approach, and thanks to their work and their resolution of Rogness conjecture, so Rogness conjecture, in Rogness conjecture, this first homology and higher homology of GLN with its coefficients appear as a pretty natural kind of part. And Rogness conjecture Rogness picture is closely related to algebraic case theory from the very beginning in rank filtrations there. And Rogness himself has conjectured that this or related objects he had should be somehow connected to polylogarithms, but I never heard of that. I was not aware of that until this picture was explained to me. But I think that the key part which allows that to happen is kind of a resolution of one of Rogness conjectures by Kupers, Galatius, and Randall Williams, which kind of explains that Rogness picture is much simpler than I think originally was expected, and that allows things to become so concrete. So that is, and then basically we started to discuss how the connection with polylogarithms might work. And at some moment, Ismael Sierra, my other collaborator, explained to me that this object is kind of interesting and they have a natural equal algebra structure there, but don't know what to do with it or how to compute it. And then since I knew that in polylogarithms we hope to get an equal algebra, we started to compare them, and sort of at first there was no reason for them to be connected at all. But now I can explain. Now I will construct a very elementary map for Q, like from one to another, which is surject, like images polylogarithms. So
what is tensor 2? Would I think that if I have two simplices, I have to think to the cohomology of the complement of one modulo the other?
So that is a question which I don't quite know answer on. So our motto polylogarism seems to be extremely closely related to it, but not quite. The natural elements, so if it were H0, that would be probably the case, but H0 is trivial because you allow arbitrary degenerations. So I don't quite know a good integral presentation for these elements. Let me put it this way. So actually what you get is polylogarithms, not an integral. So that's strange. Okay, so let me explain a special story for Q in the remaining time. So, and it's also related to polylogarithms, but in a very different way, apparently. So at first it seems that it's totally different story. So let me state a theorem which is in this joint work with Charlton and Radchenko, and this theorem is completely elementary, but it was a motivating topic for us. So in this multiple polylogarithm business, important thing is that a priori you have functions labeled by many variables, indices, and you can sometimes express one through the other. In particular, for instance, in weight 3, you can express everything through function of one variable, through D3. But in higher weight, it seems to be more complicated. And but at some moment, we came up with a conjecture, which to us was very surprising, that every multiple polylogarithm of weight n and depth k can be expressed through, I will explain in a second what I mean, through just one function where you take polylogarithm, where you take the first argument pi, but everything else is just one. So what I mean by that? So you take arbitrary multiple polylogarithm, for instance, something like Li to 2. So Li to 2 is a function of two arguments, but there should be a formula which expresses it as a certain combination, Q rational linear combination of functions Li 3, 1 with certain arguments. So a priori, you would not expect that at all because the relations between different indices kind of is complicated. But actually, what we understood is that this Goncharov has this depth conjecture which predicts how, like, when elements of this Lie coalgebra of polylogarithms can be expressed through lower depths. And you can kind of apply it, and if you believe in his pictures, you would get that conjecture. But to us, it was pretty striking because it seemed to be way too strong. But then we started to find such identities, and I wrote down an identity on the board which expresses Li to 2 as a function of Li 3, 1. But I mean, already in weight 3, in depth 3, they become extremely large, so they have thousands of terms. But what is interesting is that not only you have such identities, but also if you look at their arguments, if you think of AB as a point of a torus, two-dimensional torus, then basically all elements here are also kind of functions on a torus, except sometimes you have roots but they are kind of monomials on a torus. They're of monomial nature. So at that moment we started to kind of try to think about what in general can you say about polylogarithms where as arguments you get monomials from a torus. And this topic was studied by Goncharov in quite much detail in a work which seems to be kind of unrelated to his work on multiple polylogarithms originally, and more related to GLNZ homology and correspondence between multiple polylogarithms and truths of unity and local systems on modular manifolds. So kind of different array of his work. Eventually we came up with the following kind of answer to that, and let me just formulate it as a theorem. So this theorem implies this result almost immediately. So the core is the theorem which I will formulate.
No, I'm confused. You are with Q now? Yeah, or no working over Q?
No. So far Q didn't appear at all. So far I just have polynomial. So I started to work with a torus suddenly, kind of polynomial where all arguments are, on a torus. Sorry, before the theorem, I need a definition, kind of a little technical definition. So let's take a torus, which is an algebraic torus of rank k, and then I can define a vector space Ln of the torus. So this will be my space of polylogarithms on the torus. Let me define literally what I mean by that. So I take the following thing. So if I have a torus of rank k, I have isogenes from a torus to itself. So
it's multiplicative.
Yes. Oh, sorry, sister. Yes. Sorry. Yes. So I have isogenes of a torus. So I have isometries given by GLN-Z group, but also, isomorphisms, but also I have isogenes which I can represent by integer matrices with integer arguments, invertible matrices with integer arguments. So let me take the space Ln of T to be a Q-span of functions where I take multiple polylogarithm of weight n of just arguments x1, xk, which are just coordinates on my torus. And I take push forward with respect to isogeny over all isogenes. So elements here would be polylogarithms where I plug in arbitrary monomials, which generate the lattice because they are push forwards with respect to isomorphisms. But also I would have things like this, for instance. So if you look at what appears in here, you see that actually there are things like so sort of the sum of two polylogarithms comes from polylogarithm Lie-3-1 of AP if you just take a push forward with respect to some nice map of degree 2. So I wanted kind of a space which involves all functions in this formula, so that's the space. So kind of polylogarithms where you allow to take, you close polylogarism under all isogeny and take what you get.
How do you handle that polylogarithm are not are defined up to monodromy?
Right, so technically I would look at the corresponding framed mixed state motives and work there. So 2 pi I kind of ideal. So in this, yes, so in this way.
So you don't neglect lower weight or things like that.
So I will in a second quotient a little bit further, but so far I just take those. So what I will neglect, I will quotient by objects of depth less or equal than k minus 1 of the same nature. So I can take less number of variables and quotient by that. So this I kill. And also I kill elements which look like logarithm of a character times anything else. So I kill kind of space which is spanned by multiples of just logarithm of a character for technical reasons. So this gives me a vector space, and this vector space, there is a tiny important detail. So this is a GLNQ module now. So a priori that's not completely obvious because you have an action of isogenies. And to show that it extends to a group action, you need to show that a diagonal matrix acts by scalar. But that's true due to distribution relations for polylogarithms. That literally says that if you have a cover and you have just diagonal matrix defining it, then your polylogarism will overscale, and so it means that you can extend this to GLNQ module. So now so here I don't quotient by products. I can, but let me maybe not do it. So the main theorem here is that the main theorem here is a complete description of this. So the theorem is so the theorem also with Charlton and Radchenko is that there exists a unique GL KQ equivariant map, equivariant isomorphism between the following two spaces. So I want to describe my space L and T, and what it maps to is so I take Steinberg module of Q, tensor squared, maybe let me just write it explicitly, tensor Steinberg module of Q, and then I also have weight which can be higher than K. So I also need to take symmetric power of the vector space. So this will be in charge of weight. And the statement is that this is an isomorphism, and let me tell you where a polylogarithm goes. So if I take polylogarism Li and 1 and K as an element of this vector space, so it goes to the following element. So I need to take, so this is just before applying isogenies, so just one polylogarism. I take the standard basis. It gives me an apartment in the first Steinberg module. And then I take another element which looks like E1, but then maybe E2 minus E1, E3 minus E2, EK minus 1. So this is a geometrically a little bit strange configuration, which looks like in P2 it will be a picture like this. So that is the picture. And then I need to tensor multiply, and I just take a kind of a naive symmetric power element, which is encoding my weights, little numbers in one. So I have some product of this basis vectors to the powers k minus 1. You can.
And if I made like square root x1 on the left,
square root of x1. This you cannot do. You can take square root of x1 plus the same thing with minus square root of x1. You need to take because you do isogeny.
And what would happen on the right?
You need to take a matrix which will look roughly like 2, 1, 1, 1, 1,
And you
and then you just act by this matrix here. So
Good.
right. So that's not yes. So this uniquely defines the map because you by definition this is a cyclic module generated by one element. What is not obvious is that this map preserves any that sends relations to zero. That's not.
But also you're saying
What's n and k? Or is n equals to k?
So K here is a, sorry, K, maybe let me put K here. K is a K-dimensional torus, C star power Q. So this gives a complete description of this polylogarithms on a torus where you additionally assume that, I mean, with a little restriction. So you take this kind of polylogarithm images under isogenes.
But this also kind of says that there are no other relations, so to speak, besides those that are manifest on the right-hand side.
Yes.
Is that right?
Yes, it describes all generator, like it describes all relations. Well, I mean, it's not literally true. So we'll discuss relations in 1 second. So in a sense, that tells you what is the module. But if you want to understand all relations between multiple polylogarithms, we can do that, but it's actually more interesting.
But for example, this, this Abel relation isn't manifest on the right-hand side.
So it will appear in a second, but for now it has nothing to do with it because Abel relation just does not live in the realm of the storic polylogarithm on a torus.
Yeah.
So far there is no Abel relation, but I kind of promised there. So this is a theorem, and let me just say that one thing you can have here, kind of for obvious reasons. So you can see that if you take the case when n equals to k, you don't have symmetric power anymore. So the left module is by definition generated by one element. So it's not surprising that coinvariants of the right-hand side are trivial. And this is exactly the theorem which I mentioned before, which appeared in the work of Kupers, Galatius, Randall Williams a few years before for arbitrary fields. But the proof we have also works for arbitrary fields. So it's actually it's not too far off, more or less the same proof, but the interpretation of elements of this module as having to do something with polylogarithms that is surprising.
Reading. What symmetric power do you take?
So you take symmetric power n minus k, where n is the weight. So it means for n equal to k, you don't have symmetry. Okay, so now in the remaining couple of minutes, let me try to describe why this gives you a map from H1 of GLN Steinberg to polylogarithms. So the argument is kind of very elementary, but it's a little bit hard to write on the board. I will try. So to connect it with the previous story, my goal is to explain why there is a map from first homology of GLN Q with coefficients in Steinberg L and of Q, which is essentially, you can think Steinberg tensor Steinberg. So this is extremely close to this module L K of, sorry, L, let me do K here, L K Steinberg K. It's extremely close to L K of the torus C star power K. So there is this difference by quotient by products, let me ignore it. It's not relevant. And I want to show that there exists a map from here to the Lico algebra of mixed state motives over the field Q, and the image is actually multiple polynomials. So that is what I want to show. In particular, I expect to see here the 5-term relation and 22-term relations. They should somehow come from the storic polylogarithm combinatorics, which is a little strange. Okay, how to construct a map from H1 to something. So we need to compute H1. So how we do that? So this theorem on the right-hand side tells me that there is a surjective map. So you have Steinberg L of Q, but there is a surjective map from the free, the free module on GLN. So just free module, and this map takes a matrix and sends it to kind of this image of the maybe pushed forward of the multiple polylogarithm V11 of x1, xk element corresponding to that here, which you can think, of course, as a pair of apartments. But it's instructive to remember that this is related to polylogaritms. So you have that, and then you have a kernel. So kernel is literally just relations between multiple polylogarithms. So you are curious, what are relations between this kind of a very special apartments within Steinberg tensor Steinberg? So a priori, not obvious question. So now, what does it mean to construct a map from H1 here? So we need to construct a map from this Q of GLN Q from this free kind of module we need to construct a map from I to this mixed Tate model liquid algebra. But this map should have a property that it factors through coinvariance, meaning it's GLN variant. So you want to construct a GLN variant map. So how to do that? Again, what is I? So I is an identity. So this is a relation between multiple polylogarithms monotomes. So the map here is constructed in a very explicit way. Let me just say what it does. But then it's not obvious that it's invariant under the group. So the map is, it's defined on generators here, and what it does, so if you have an element here, so you take an element in Q of GLN Q, so which you think of just a collection of vectors, V1, Vn, and Vk, and then you do the following. So you choose, let me maybe erase something. So the map is constructed as follows. You choose an auxiliary linear function on your vector space, just without any restriction, non-zero linear function. So you choose phi in linear functional on f power b, non-zero linear functional, and then so the map from I to polylogarithms is as follows. So I, after all, sits within this Q of GLN, GLK. And then what I do, so I take an element here, which I can think of just a collection of vectors. So I have a collection of vectors V1, Vk. And then I send this element to iterated integral in the usual mixed motive sense, where my first point is infinity, which is well defined if you are working modular products. In the liquid algebra, there is a way to make sense of it. And then you just take phi of V1, phi of V2, and so on, phi of Vk, 0. So it's integral from infinity to 0, iterated integral with the poles, which are just this linear functional applied to a bunch of vectors. So in a sense, it's most naive thing you can do. So you had an elements which are just linear combination of matrices. You just applied, you took like first coordinate essentially of each vector and wrote down some of iterated integrals. So this is kind of a tautological map almost. But what is not obvious is that if you have an element which lies in this I, which is this kernel of the map, so if you have a certain combination which vanishes in the Steinberg, then this map is independent on the choice of the linear function. So kind of the idea is that if you have an element A which lies in the kernel of the map from Q of GLK Steinberg module, L, Steinberg LK, then the image of A is independent on the linear function. And let me say that in a sense, that is not only it's a theorem, but also it's a source of actual equations for polylogarithms. because it tells you that if you find any particular identity in Steinberg L between these elements, you can now vary linear functional and you will get equations. And it's a theorem that all equations come from Z, and you get a 5-term relation for n equal 2 and the 22-term relation for n equals 3. But you get similarly completely explicit equations for higher n as well. So you have just complete structure. I'm over time. So there is a one-line argument why it's independent of phi, but shall I say it?
I think you should say it.
Okay, just one, like what is the style of why this is independent of phi? There is a very elementary reason. So the reason is that so multiple polylogarithms are, when you view them as elements of this Liku algebra of mixed state motives, are kind of continuous functions, mostly. Except that if you take a polylogarithm 1, 1, 1, 1 of x1, xk, this function is continuous kind of everywhere except point 1. Point 1 is a very singular point. So in particular, if you want to take a limit at xi is going to 1, so you better assume that xi go to 1 along certain curves. If you take polylogarism with higher indices here, or if you take polylogarithms where you take roots and you take certain roots of unity, like what we have here sometimes, this will be continuous at point 1. So only this Li 1, 1, 1 is discontinuous. So now, when you take an element in the kernel of this map, by definition, that gives you an identity between multiple polylogarithms on a torus. But this identity actually involves tons of summons. Some of them will be actually indeed looking like polylogarithms like that, but some of them will be actually lower depths, which I was ignoring when I was defining this L object. Some of them would have these roots and roots of unity. So there are lots of things. But the observation is that actually for each term in this Q of GLK, there will be exactly one summand which is not continuous at 1, and everything else will be continuous. And we work modulo some lower depths and so on. That's also all continuous. So it means you can take discontinuous part, and because it's identity equal to continuous part. So it means sum of discontinuous terms is continuous at 1. That's what implies the independence of the functional, because the relation is that taking a functional and applying this map explicitly just you can take a functional as kind of a tangent vector to a torus at 1 and taking the limits. This will be this map. So so maybe helpful computation is that, for instance, limit when x goes to x equals to t power a and y equals to t power b at 1 of Li 1, 1 of xy is actually dilogarithm of 1 minus x over 1 minus y. So that's an easy computation, but kind of that means that basically all equations for polylogarithms will come from equations on polylogarithms on a torus modulo lower weight by this kind of limiting procedure.
So what is that limit taken over?
So it's a limit when t goes to 1 along a curve, 1 minus a, 1 minus b. So the philosophy is that kind of an interesting equations for polylogarism come from the storic monomial equations when you start to take limit at 1. Sort of. But not literally, you need to take discontinuous terms and take limit at 1, and it will be continuous, and that's where equations come from. So that gives you a map which is well defined, and one can show that for Q, but then the formulas, to be honest, they make sense for arbitrary field. You have that formulas, you don't have limit argument. So you can try to kind of mimic somehow, find some different reason why it's independent on the vector. And that is kind of a different story, but thank you very much.
Questions? Can you make this Abel relation transparent by means of this last equality you wrote down, for example?
That is a little hard for the reason that if you want to get the Abel relation, so firstly you need to assume, like technically, that everything here is a rational function. But also, kind of this things for rational functions would come from identities which involve summation over like roots and covers. I can show explicitly, we have in a previous paper of ours an equation. So So in the previous paper of ours, where we proved there's this conjecture that polylogarithms of depth 2 can be expressed through Lie, whatever, something 1 on a torus by writing an explicit identity. So this is certain explicit identity on a torus of polylogarithms with roots. And there is an identity like that, which if you apply this argument, takes the limit and sees that it's independent on the vector, that will be literally 5-term equation relation. So I can show it after the talk. Yes.
For the 5-term relation, this interpretation in terms of cross ratio. Is there a similar interpretation for the
Yes.
20-term relation?
Yes. So I think I can say, so you have identities. So like frankly speaking, from our story, we get a slightly different identity, which can be shown to be equivalent. So the identities which you actually get are of the following kind. So first is they all live on P2. So they all live on they depend on a configuration of points on P2, not P1, but P2, which just in case of dialogarithm appears to be the same. And then they are all, I can just write down all these equations, sort of say where they come from. So the way they come from is as follows. So I will describe a combinatorial procedure. So you take an iterated integral. And then you can compute the corresponding element in the bar construction, this kind of symbol now. So you will have a certain long sum where you have elements like T, I don't know, I will write something silly, but like T1 minus T2, tensor T2 minus T3, tensor something, T1 minus T4. You have a certain long sum of such things, which represents a bar construction element whose corresponding iterated integral is that. So now you take this element and then you do the following. So you take, so the equation will look like that. You take the sum of it, you take iterated integrals. You take for each term, you write down an iterated integral, and the iterated integral is from infinity to 1. And for every monomial, you write down a fraction of Plücker coordinates on P2. So you take a bunch of points on P2, which is indexed by the same indices as here, and you kind of write down certain fraction of Plücker coordinates. So you write some of the iterated integrals where there are as many terms as there are in the bar element corresponding to iterated integral, and also it depends on two auxiliary points to make out of two indices kind of a triple Plücker coordinate. And then the statement is that this thing is actually it's actually sort of some function of x minus some function of y. So though a priori x and y appear in every term, you can write it as a difference like that. And this function is basically just iterated integral pulled back to P2. So that is this. So basically, the equation has as many polylogarithmic terms as there is in the symbol of the usual iterated integral in P1. And that is essentially one can show that this is the only generating relations of this H1 GLN Steinberg.
Okay. If there are no other questions, let's take